Alright, quadrilateral ABCD with point A at -3, 5, point B at 1, 4, point C at 3, 1, point D at -1, 2, and point E at 0, 3. Prove quadrilateral ABCD is a parallelogram. Harold writes the following proof for this problem. So this is his proof, and what mistake, if any, did he make in this proof? So the first thing that I'm noticing is in his picture he has diagonals from A to C and from B to D. So, and I'm looking through his reasons given: distance formula, transitive property, definition of congruence, definition of bisect. If the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. My first question to myself, if I were going to be doing this, is that true? Is that if diagonals of quadrilateral bisect each other, then the quadrilateral is a parallelogram? The way I would check it is I would first jump to the key terms, click on parallelogram, and it just is telling us that a quadrilateral with both pairs of opposite sides and are parallel. So that doesn't help me with this theorem. So I'm just going to scan back up through here. Since it's not on the key terms, I'm going to scan through this and look for red boxes, because red boxes have our postulates. And if you notice this first one, it says a parallelogram is a rectangle if and only if its diagonals are congruent. Okay, so that's talking about a rectangle. It says if parallelogram ABCD is a rectangle, then segment AC is congruent to segment BD. So segment AC is congruent to segment BD. We're still just trying to look for a parallelogram based on its diagonals. So this one is saying if a quadrilateral is a parallelogram, then its opposite sides are congruent. So it's still not right there. So if we keep looking, I'm not seeing it so far. Checking, there's our distance formula, and we're back into triangles. So I did not see anything where it stated that if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. It says in reason 6, Harold should have used the theorem stating that quadrilateral is a parallelogram if opposite sides are congruent. That is the only one that has been showing up. So if we go back up here, another way we could check is to Google it. We could say if, I'm just going to copy this and see if this is true, because it wasn't listed in. For quadrilateral to be a parallelogram, some other properties are required. Opposite sides are equal and parallel. Opposite angles are equal. Diagonals bisect each other. So yes, it is that they do, that this is correct. And I'm not sure why it is not listed in our quadrilaterals in the coordinate plane. Maybe I just scanned too fast and did not find it. So that could be a possibility. So that is true. So now that we know that that is true, I would go just, did Harold didn't make any mistake? All of his statements are correct and justified by the reasons provided. So to eliminate the option that it should have been 2 or it should have been 13, we would just use the distance formula. B would be our x1, y1, and E would be our x2, y2. And so then when we do our horizontal distance, that's the difference between our x values. So it would be 0 minus 1 being squared, and our vertical distance is the difference in our y values, which would be y2 minus y1, so 3 minus 4. And then jump over to your calculator, square root, parentheses, 0 minus 1, close parentheses, x to the y squared, not close parentheses, plus parentheses 3 minus 4, close parentheses being squared, and that equals 1.41. Now the question is that equal to the square root of 2? So one thing we can check is we hit square root of 2. Oops. Square root of 2, and that equals 1.41. So yes, it is the square root of 2. That was correct. The next one is to have that the square root of 13 instead of it should be 13 instead. So the other way we would do this is again use our distance formula and now CE. So C would be our x1, y1, and E would be our x2, y2. So again, in our distance formula, the horizontal distance is the difference between your x's, so x2 minus x1, so 0 minus 3. Our vertical distance is the difference between our y coordinates, so y2 minus y1, so 3 minus 1. Jump over to the calculator, square root, parentheses, 0 minus 3, close parentheses, x to the y squared, plus, parentheses, 3 minus 1, close parentheses, x to the y squared. 3.6, so this equals 3.6. So now how can we check to see if it equals the square root of 13? Well, we just type in square root of 13. It does come out to be the same decimal, same number, so that is correct. So Harold didn't make any mistakes at all. He wasn't using that opposite sides were congruent. He was using that bisect. So E bisects segment AC and E bisects segment BD. So that is how he was finding that out. So everything's good with that one, and I hope that helps.